Good morning again, everybody. As always, a pleasure to be on the stage introducing our fantastic speakers. Today, they have a little bit longer, so they will not quite have the 45 minutes of a standard lecture, but it will not be quite as short as yesterday's 3-minute whirlwind talks. So today, the speakers have been asked to construct a 15 or so minute talk. There will be 4 of them in the session. We may have an opportunity for questions. I'm going to emphasize may. It depends on how the timing goes. But if we have time, I'll do 1 or 2 questions. But as always, please do speak to the laureates. Afterwards, there will be a coffee break following this morning's session. For instructions for the speakers, you will again need to come and stand at the podium so that you have the microphones there. That's the problem with having so many speakers at once, is we can't mic you all up. Okay, so the first speaker today is Martin Herrer. Martin was awarded the Fields Medal in 2014 for his outstanding contribution to the theory of stochastic PDEs. And this is a topic I've had the pleasure of discussing with Martin in a couple of YouTube videos, which I've recorded at previous HLFs. And one of them basically consisted of us playing an infinite game of Tetris for about an hour and talking about what that had to do with mathematical structure, which was highly entertaining. So please do ask Martin about infinite Tetris. It's amazing. And I also recently discovered that Martin enjoys making kimchi. His own homemade kimchi is a sort of hobby of his, shall we say. So if you are interested in kimchi and want a recipe, I imagine Martin could probably share with you his special recipe. So today, he will of course not be talking about kimchi, he will be talking about taming infinities. So Martin, the stage is yours.
Thanks a lot, Tom. Right, so I don't know if there's a clicker or does it get clicked automatically? Hopefully. I don't see a clicker here. Anyway, right, so the plan is that this Sparks talk is sort of a teaser for the master's lecture, or whatever they call it, which I'm going to give at 11:30. So the idea is that here I give you a bit of motivation, and then if you want to know more about it, at 11:30 I'm going to present an actual specific piece of mathematics, sort of self-contained, which is related to what I'm going to talk about now. Cool. So it's even a clicker. It even works. Okay. Right. So the motivation I want to talk about today is essentially dealing with some infinite quantities that originally they showed up in quantum mechanics. And so that was back in the days when people were developing quantum field theory, right? So it's like in the early 20s or so, people had just started to figure out what quantum mechanics is about. And then they wanted to actually apply it not to just, 1 or 2 particles, but to an actual field like the electromagnetic field or something like this. And they did what physicists usually do, right? I mean, when you want to model some piece of reality, what you do essentially is that you guess a model, right? So you don't, at some point you have to just make guesses, right? I mean, like you always think physics is about derivation of things, but you have to start from somewhere. So if you do really fundamental stuff, you actually just make guesses. So you make a guess for the form of your model, but then typically your model, you have a guess for the form of the model, but then it has a whole bunch of parameters. And then those parameters, you can't really guess them, right? So say mass of the electron or whatever, like these kind of things, speed of light, that sort of parameters. You don't have a guess, you just leave them as constants. So you really don't guess one model, you guess like a whole family of models that depends on a bunch of parameters, right? And then what you really do is you do experiments and you try to match the model to experiments. And then you say, well, you do one experiment and you see, well, you have your big bunch of models. You see which ones match. Well, that gives you sort of a one-dimensional constraint, so that would give you maybe some sort of hypersurface in your space of models, and then you do another experiment, you get more constraints and so on. And once you've got kind of more experiments than parameters in your model, with a bit of luck, you've kind of narrowed it down to just one particular model, so you've determined all the constants that make up your model, and then you can actually make new predictions, right? So you see one really important takeaway message here is that if you want a physical theory to be useful, it better be the case that it only depends on finitely many parameters, because otherwise you have to first determine all of them before you can make predictions, and if there's infinitely many of them, you're sort of never done actually determining the parameters, and so your theory is sort of never useful, right? Anyway, so that's kind of what you do in physics in general, right? So that's just a general procedure of how physics works, basically, theoretical physics. And now in this particular case of quantum electrodynamics, people came up with a model. The model is sort of complicated, and so you actually write it up as a kind of Taylor expansion in one parameter, which is called the fine structure constant, which is about 1 over 137 or something. So it's one of the very few physical constants that doesn't have a unit. So it's really an actual number, right? Like in every unit system, it's 1 over 137. And so you write it kind of as a power series in this fine structure constant. And so what they did first is sort of determine the first term of that power series and sort of matched experiments reasonably well. But then what Oppenheimer figured out, so it's the same Oppenheimer as, the one maybe you saw the movie about. So what he figured out is that, well, if you want to go to the next order, what you find is that the coefficient in front of the next order is actually just infinity. And you're like, okay, that's really bad luck. So the whole thing breaks down, right? So what you do, so maybe you think, okay, so like the whole theory is kind of rubbish, so you have to restart again. Or, you are kind of a very smart person, like these guys, well, about half of them got a Nobel Prize, I guess, or maybe even more. And you sort of figure out recipes to kind of just throw away the infinite bits you don't like and extract finite quantities out of it. And amazingly, that actually worked. I mean, people first found that a bit weird, right? So like here's what Dirac said. This is just not sensible mathematics, which involves neglecting quantities very small, not neglecting them because they're infinitely big and you don't want them. Sort of, you can understand where he's coming from. Or here, Feynman, who said the shell game we play is technically called randomization, but no matter how clever the word, it's still what I would call a DP process. So, people were a little bit worried about this sort of cooking recipe that they came up with for throwing away these infinite quantities, but it really worked somehow. So now, why does it work in some sense? So what's the general principle behind this, right? So what is this randomization thing? So, I mean, at the time, it was sort of, originally, it was really kind of a cooking recipe. In some sense, what people did is they say, you look at how this infinity shows up, like, right? You compute that first term in that power series and you see, it's actually some complicated integral of something. And then the integrand diverges somewhere, and that's why it's infinity. And then you say, well, okay, so what I'm going to do is I just pretend that infinity is finite. So you have that divergent integral. It's infinitely big. You just give that infinity a name, and you add it in as a new parameter in your theory. Right? Okay, that sounds like cheating. But then what you see is you say, maybe there's another term somewhere, and it also diverges, but it sort of diverges in the same way. So it's maybe not exactly the same function, but if you compare the two functions, maybe one is like, twice the other one plus a smooth bit or something like this. And then you say, well, the integral of that one should be twice the integral of the first one plus the integral of the smooth bit, right? And so if you're lucky, there's only sort of finitely many ways in which these things can diverge. And so then you've just added finitely many parameters to your theory that represent these sort of finitely many infinite quantities. And then you're again back in a theory with finitely many parameters, and then you just do experiments to determine them, right? And then you can make predictions. Okay, so that's basically how the cooking recipe worked in a nutshell. And if you want to sort of understand, like later on, what was understood is that in some sense the procedure is more like this. So that we're going to try to give you sort of a mathematical cartoon of what's sort of going on. So a physical model, what is it? It's essentially a function that has two types of input, right? The first type of input is the parameters of your model, and the second type of input is the description of your experiment, right? And then it spits out the outcome of the experiment. Okay, so that's a sort of super general cartoon of what a physical model is, right? So it's something that you can tell it what experiment you're doing, and it spits out the prediction for the experiment, but it also depends on a bunch of parameters which sort of describe your theory, right? So here I call lambda the parameters that describe the theory, and E, like experiment, sort of the whatever that describes your experimental setup, right? And so you have a function that is supposed to give you predictions, but, you know, like in our case, that function isn't really well defined because it wasn't actually a function. It was basically a sort of procedure for computing terms in a power series, and it was supposed to compute big integrals, and they actually diverge. And so that function isn't really well defined. I mean, it just gives you infinity or something. And so what really happens there, it's more like what you're going to do is you say, well, I'm going to somehow regularize my theory, which is saying, well, sort of what happens is that the regime in which things diverge, you say, well, that's maybe a regime in which my description actually breaks down. It's maybe what happens at really tiny scales. And so I'm going to just change the theory in some way. So I add now a third sort of set of parameters and a small parameter, right? So there's a small epsilon now, which is somehow, say, like the size of this very small scale at which you're going to modify the theory. And now you've added a third set of parameters, which are called U, which is sort of the unphysical parameters which describe, you know, how you're going to modify your theory at small scales. But now, of course, you know, now you've somehow turned it into a much more complicated theory where you've sort of changed completely what happens at some very arbitrary kind of small cutoff scale. And hopefully what you would really want to do is send that small scale to zero and get some kind of idealized theory back. And of course, the whole problem that I described to you with these infinities is that if you just naively try to send epsilon to zero, things simply blow up, right? So what you want to do instead is that you simultaneously send epsilon to zero, and you do a change of parameters in the space of parameters of the theory, right? So the lambda space, which is the one that had the sort of original, like macroscopic kind of parameters of your theory, there you do a change of variables. So you reparameterize that, okay? But it's really just, you don't change the theory, you just parameterize that space of parameters in an epsilon dependent way. And possibly also in a way that depends on the unphysical variables that you've added. And then what actually happened in all these, you know, in these theories where renormalization works is a kind of a miracle, which is that you can do this in such a way that as epsilon goes to zero, you do get a finite limit. And the finite limit that you get, furthermore, becomes independent of these unphysical variables that you've added, right? So you've basically, you change the theory at small scales in some more or less arbitrary way, and then you send the scale to zero, and then just by reparameterizing somehow the original sort of parameter space of your theory in the right way, you get a limit which is finite and which doesn't depend on these new variables that you've added. Okay, so that's somehow the general principle, and you know, it really works. I mean, like, so Toft here, he got the Nobel Prize for showing that in some sense this kind of procedure works for the standard model, which is like the model that's supposed to kind of describe reality except for gravity or so. And the, so what I'm going to talk about, so this is an old story if you want, in some sense, right? So like renormalization, people kind of started figuring that out in the late 20s, early 30s, and then by the 40s, 50s, with people like Dyson, Stuckelberg, whatever, they had a really pretty good understanding of how this thing works. So it's an almost 100-year-old story. But much more recently, we've sort of realized that actually in probability theory, there are a number of problems where very similar kind of infinities show up. And you can adapt these techniques of randomization. So that cartoon picture that I just showed you, that actually still works. Now, the details are very different. So like the way of implementing that cartoon picture is very different in quantum field theory and in probability theory. But it turns out that it still kind of works very well. So for example, here one example which I like is this example of interface growth models where, now has nothing to do with quantum field theory. It's just completely classical kind of thing. You have a interface that separates two regions. So for example, one experiment, so the thing on the right is an actual picture of an experiment where people take a liquid crystal and it comes in two phases. You sort of zap it with a laser beam, it changes phase, and then the phase expands, and you keep track of the region that separates the two phases, and it moves, it expands, so it moves as a function of time. And it's also slightly random, so it kind of starts fluctuating more and more. That's why you see that, colorful picture on the right, where color represents time, if you want. And you see on the top line, it's kind of not a straight line, but it has these sort of random fluctuations, and you want to have a probabilistic model that kind of describes these random fluctuations. So you can come up with a lot of sort of toy models that describe that. Then you can prove that in certain regime, this fluctuating interface is described by a PDE, which I wrote down here, which has a stochastic term. So it's for those of you who followed some PDE courses, you see something like a heat equation here, plus a nonlinear term, which is somehow the slope of the solution squared, plus this psi, which represents the randomness. So this, you should think of it as saying, well, at every point in space and time, you sort of flip a coin and it tells you whether you push a little bit up or you push a little bit down. So that makes the whole thing very irregular because it keeps on being pushed up and down everywhere at the same time all the time. So the solution becomes very rough. And if you kind of try to analyze this equation, what you find is that, well, if you forget about the nonlinear term, right, if you just take the heat equation plus the noise term, you wouldn't expect solutions to behave better than that in a way. Then for that one, you can already show that at any fixed time, the solution is sort of so wiggly that it doesn't actually have a well-defined slope at any point, right? It's kind of, so in technical terms, it's just about not Hölder half, and it's definitely not differentiable anywhere. So it really doesn't have a slope. In some sense, the slope is like infinite at every point because it moves so fast, kind of up and down. And so then that nonlinear term, which is in red now, it's kind of nonsense because that tells you, well, take that slope and square it, and that's one of the terms on the right-hand side of your equation. Of course, if you have a slope that's sort of vertical at every point and you square it, that's kind of identically plus infinity everywhere, and so the equation is just total nonsense. And so the idea is the way you should think of it is that, well, there's this constant on the right, this minus c, and you would want to take that constant also sort of identically equal to infinity so that it sort of cancels out the infinite part of that nonlinear term, but in a way that doesn't cancel it out completely. It just cancels out sort of the infinite constant part, and there's a finite sort of fluctuating part that remains, and that's how this equation should be interpreted somehow, right? And so if you're interested in the master course or lecture or whatever it's called, I'm going to, give you sort of a little explanation of how do you actually set up a calculus which allows to actually give a meaning of these type of equations so that you can get, the proper mathematical interpretation of these equations, which is furthermore consistent with, the actual physical model, so that it gives you sort of the right solution which really describes these kind of situations. Okay, so if you're interested, just come at 11:30. Okay, thanks.
I think in the interest of time, we may have to push questions for Martin to the coffee break, or, go to his masterclass as he told you. But thank you again. Fascinating as always. Okay, our second speaker in this morning's session is Andrei Okounkov. Andrei was awarded the Fields Medal in 2006 for contributions bridging probability, representation theory, and algebraic geometry. And in my research, in preparation for this session and introducing our speakers, I found an old BBC article from 2006 when Andrei was awarded the Fields Medal. And he was asked about his thoughts on receiving such a prize. And this is his quote, which I think is rather thought-provoking. I suppose we all will have to exhibit exemplary behavior from now on because a lot of people will be watching. Which again, I thought is quite a thought-provoking and interesting way, perhaps that I hadn't thought about, when you receive a prestigious prize relatively early in your career. So Andrei today will be talking about partitions. So Andrei, I'd like to invite you to the stage. There you are.
For the record, thank you everybody for being here. So for the record, I never said that. The BBC totally invented that. I'm sorry that is being repeated by people. Oh well. So this is. I was asked to give maybe a brief advertisement for the masterclass today, and so I don't even know what the masterclass is supposed to be. Everybody in my family enjoys the kind of masterclasses that you can get at maybe a Museum of Arts and Crafts or at a cooking school. It's something where you can have a hands-on experience trying to maybe an artistic technique you never tried, or difficult to try at home, or try making use some culinary equipment that's also very difficult to try at home. And my master class would be, I'm planning it in this hands-on style, where you can just try and see if you like it. And this is supposed to be, and for instance, I myself would be very curious to try welding one day. Maybe in one of these forums later, we'll be given an opportunity to actually go to a factory and try something like that. But of course, my masterclass will be a lot more relaxed, and I also think that this is, we keep saying math is exciting, math is energizing, and so on and so forth. But there's also, in math, it's also important to have quiet moments, just quietly reflect. In fact, we sort of, in addition to trying, doing some kind of hands-on work, and it's also good to have quiet time to reflect on something. So instead of trying to give a spark talk, instead I'm going to give like a spa talk. And so this talk would be about partitions. And I will mainly talk about the word partitions. And math is not only, it's among other things, the role it plays in science, it provides a universal language to all sciences. And it's very important to know, if you're learning a language, it's important to know vocabulary. And it's just from knowing, so suppose you're solving some problem of theoretical or applied interest. If a mathematical object such as a group or graph or manifold or some other basic structure comes up, just from realizing that you're dealing with it, it really helps. It really helps you orient yourself in the space of mathematical ideas, know where to look for the results that you can use, and so on and so forth. And the word that we'll be talking about today is partitions. It is much, much, much simpler. I assume all of you know well, not assume, I hope all of you know what's a group or what's a manifold or and so on and so forth. But I'm sure all of you know what's a partition. And but nonetheless, let me remind it. So a partition is simply an ordered collection of positive integers, which you think of a sum of, so if you have number 10, you can partition into in 5, 3, and 2. And you can visualize it by putting 5 spa stones, 3 spa stones, and 2 spa stones on top of each other. So that's a partition of 10. And you can write it as either 5 plus 3 plus 2. That's got to be the simplest formula. You'll see the whole conference. So, or you put brackets and parentheses. And then instead of stacking stones, we most of the time people draw a partition as 5, 3, 2. They draw it something like that. And is there a pointer to this? It points somehow this. Yeah, does it point or? No, it doesn't. That's too bad. But in an attempt to maybe connect this kind of kindergarten mathematics to the grown-up mathematics you just heard about, if you imagine this partition being not 5, 3, 2, but a very, very large partition, so you'll have if you represent it in the maybe a third way, you'll see a very, very complicated zigzag shape. And that would be, in fact, a regularization of the kind of infinity that Martin was talking about. And so it's not, it does lead to something maybe more interesting situation and basic counting. And of course, you can imagine that instead of drawing a picture of the kind, we call this two-dimensional partitions, you can have a three-dimensional object, same. I'm sure you all see the parallel, how this is a three-dimensional analog of the picture we just saw, and you can imagine a four-dimensional one, and you can many related geometrical structure. And of course, you can also consider one-dimensional partition, which is just, so if it's only one pile of spa stones, well, it's just natural numbers, so it's not. Also a very important object in mathematics. And maybe partitions first, mathematicians first looked at partition as long ago as 1740 when Leonhard Euler, in a correspondence, somebody asked him how many partitions are there of a given number? In other words, how many, like if I want to write 10, in how many ways I can write 10 as a sum of non-trivial terms. And for 10, there's 42 possibilities. That's something you can easily enumerate. And Euler thought about it and came to the following solution. He first noticed an easy formula, and that's the left-hand side in this formula is something mathematicians call a generating function. Also, I think our friends in computer science like generating functions. So if you have some unknown numbers, p of n, you can, instead of talking about an individual number, you can form an infinite series with these numbers are the coefficients, and then talk about that series. And if you write a generating function for this p of n, there is an infinite product to it, which is more or less immediate from definitions. But Euler noticed a very curious fact that if you take reciprocal of this function, they say 1 over, then the coefficients are, first of all coefficients are 0, 1, or minus 1. And in fact, they come the zeros, ones, and minus 1 come in a very, very nice pattern. And among other things, if you multiply, so what does it say? That if you multiply the function you want by this very explicit series, you get 1. And that gives you a very, very simple recursion for the number of partitions of a given number. That was Euler's solution for the problem. Very beautiful. And of course, almost 300 years later, we realized this to be a very special case of many more general theorems. Is that water okay to drink? And completely tautologically, you can rewrite it slightly differently. if instead of forming this generating function over, so you sum over all integers, you take q to the n, and the coefficient of q to the n is the number you want, p of n. Just tautologically, you can rewrite it as I'm sum over all partitions, and I put q to the size of that partition. So that's just, I don't think it's worth any further comment. But it's interesting to notice that many functions of q in other variables may be introduced if instead of just summing q to the size of the partition, I also introduce some other weight function, some other additional weight to put with the partition, some function w of partition, maybe some other parameters. And that gives an very interesting supply of functions. And what is this function going to generalize? So if you're, of course, if you look at elementary functions or kind of basic special functions, there are some of them, like the tangent, that have a pretty complicated Taylor series. So, but most of them, those Taylor series you can write in a mechanical fashion, they all fall into this general kind of hypergeometric type. So this is, I'm just saying, take an example, or exponent, or logarithm, or whatever, some function like that. This will have the shape that you're summing. Again, you have this series, you're summing over all non-negative n, and the coefficient of z to the n is some ratio of things people call factorial powers. The factorial power is just when instead of raising some number a to the power n, you multiply a by a plus 1, by a plus 2, and so forth, n times. And if we think of n as a one-dimensional partition, then you can imagine you take these terms in this factorial power, and you just you put them in boxes of this one-dimensional partition, and either way you like, you can write it like this: a plus 1, and so a plus 4, or the other way around, and this will. If you multiply all these terms, this will give you this factorial power. So that's, you can say, well, the sum on the previous slide, that was like a sum over one-dimensional partition, and then I have this silly rule of filling in the boxes. I just multiply them all, and that's my coefficient. And if you think what's going to be the two-dimensional analog of that, well. So now if I have a box in the partition, in that diagram, I have a box somewhere, previously it doesn't really matter if I counted from the beginning to the end. Now, of course, it matters. So this box you can count from the top, from the left, from the bottom, from the right. And so you get a really funny factorial analogs generalization of factorial powers. And if you now sum over all partitions, q to the size of the partition. I apologize, the size is missing in the slide. It's just q to the size of the partition. And then you multiply over all boxes some expression like that, and they go in the numerator denominator. Remarkably, such functions have really many uses in all areas of mathematics. We'll talk a little bit about them in this master class. And there's at least three, or many, there's at least three contexts in which something like this occurs. And the most direct one, this is about Fourier series or harmonic analysis, or whatever. So usual Fourier series tells you how to decompose a function in terms of characters of, say, if it's periodic function, how to decompose a periodic function in terms of characters of the group, reals mod Z, or circle group. And if you have other groups such as symmetric group or general linear group, you similarly can decompose any object you want in terms of something that has to do with irreducible representation. And for the circle group, the irreducible representations are indexed by integers. And for groups like symmetric group and general linear group, they're indexed by partitions. And so the harmonic analysis there leads to the kind of functions I've discussed. Also, partitions label a basis in certain representations. So again, representation is useful notion. And then not just the symmetric group and general linear group have representation, many other very interesting algebras have representations where partitions label a basis, and so that then what you're doing is secretly tracing, not secretly, maybe explicitly tracing, computing like a character formula for some interesting algebraic object. And maybe most importantly, and maybe that's the really generalizing the previous two things, those partitions really encode integrals over very, very important manifolds like the Hilbert scheme of points. And there the partitions label very distinguished points in this manifold. So if we have time, in the master class, we'll talk about these three origins of sums over partitions. And maybe I'll just leave you with the advice so that next time you see a partition, please recognize that it is a useful object, and it may be showing you the way to solving your problem. That's all I wanted to say.
Andrei, thank you. Because I promised we may do questions, let's do one question, if that's okay. So we're going to try and squeeze in one question. Does anyone have a question, Andrei? Or you will say something else. I'm sure
I failed, but...
No. They just want to discuss it in the masters, but thank you so much. Thank you. Okay. Right. So this now brings us to our third speaker of the morning, keeping it all fresh and fast. So our next speaker, Bob Tarjan, was awarded the Nevanlinna Prize in 1982 for his work on the development and exploitation of data structures supporting efficient algorithms, and then also the Turing Award in 1986 for fundamental achievements in the design and analysis of algorithms and data structures. And again, I did a little bit of research before this, but I've already learned that I need to check my sources better, so apologies, Andrei, for not having done that. However, I am going to trust Wikipedia, which I may regret, because Wikipedia, your page, Bob, tells me that your publications have been cited over 94,000 times, which is an incredible number. And this is the exact wording: you hold at least 18 patents. Now, to me, that suggests there might be some more that we don't know about. So maybe that would be a fun question to ask. His talk today will discuss sorting using partial information. I'd like to invite you to the stage, Bob. Thank you.
Who are these people? You know, anybody recognize either of these? So that was 1978. The guy with the long hair and the beard there, that was me. 30 years old. We were all young once upon a time, just like you. We all get nervous, just like you. And that's George Polya. He was 90 years old. I was teaching a course in combinatorics with him at Stanford. It was a great opportunity. Something to aspire to, shall we say. Let me just make a few observations here. So I do algorithm design and analysis. Over last 60, maybe 75 years even, we've come up with beautiful, efficient algorithms. Field is still young. I get asked questions all the time. Is it over? I mean, are we done? Have we made all the possible discoveries? Well, you've seen the physics talks and the mathematics talks. Mathematics has been around for thousands of years, still beautiful open questions. And computer science is still young, so we still have some beautiful questions to address. But characteristic of a young field is that we go for the low-hanging fruit, right? We don't necessarily systematically explore the design space. We get the good enough solution, but maybe not the best possible solution. And the more resources computers have, the faster they get, the more memory they have, the more space there is to play, the more room there is for good algorithms. So the design space is rich. Let's explore it systematically. So my goal, more and more, it's always been, is simplicity. I think sometimes we view complexity as being wonderful for its own sake, but I think it's more important to try to come up with the simplest possible solutions. Paul Erdős, who was a famous mathematician known for many interesting sayings, had this idea of proofs from the book. That's the book in the sky. So let's come up with algorithms from the book, the simplest possible algorithms that do the job. The analysis can be complicated. If the algorithm is not simple, no one is going to use it in practice. This is a quote or a saying attributed to Einstein. I don't know whether he said it or not, but it's worth remembering. Make everything as simple as possible, but not simpler. All right, so let's get to data structures and algorithms. The role of data structures. If we have some kind of what is computation all about? It's manipulating information, it's manipulating data. If we have some problem that we need to address, we need to somehow structure the data in such a way that we can answer questions about it, do queries, and modify it in certain ways that depend upon the problem. Often with a graph problem or a network problem or many kinds of combinatorial problems, the key turns out to be choosing exactly the right data structure to help solve the problem. So let me try to illustrate this with a problem I've been working on recently. Sorting by binary comparisons. This is about the most classic computer science problem. We're given a collection of items, n items. They're totally ordered. Think of them as numbers or strings or something. We want to arrange them in increasing order. The operation we're allowed is comparison. We can compare two items. We get the answer of which is bigger than the other one. We have to do a number of binary comparisons in order to sort all the items. Now, this is a rare problem in computer science where we actually have a non-trivial lower bound, because if we have n items, we know how many possible arrangements there are, the number of permutations, that's n factorial. If we're doing binary comparisons, we have to make a choice among n factorial possibilities. We need the log of n factorial comparisons to do the job. The log of n factorial is roughly n times the binary log of n. That's the number of comparisons we need. That's a lower bound. And there are many classical sorting algorithms that achieve this lower bound. You know them: merge sort, heap sort, which do this in the worst case. Quick sort does it in the average case. This is all standard undergraduate, by this time maybe high school, computer science. Good. But now let's ask kind of the next question. What happens if somebody gives us some information about the sorted order ahead of time? In particular, suppose we know the outcomes of certain comparisons in advance. This has got to help somehow. How much does it help? How can we take advantage of this information? So let me model this problem using graph theory. I'm going to call this sorting on a directed acyclic graph. So we're given some comparison outcomes. I'll model each one by an edge in a directed graph. So if I have x and y, and I know that x is less than y, I'll draw an arrow from x to y. That gives me something like this. So I know that A is less than D, B is less than D, and so on. This is the information that I have. There are no cycles in this graph, we hope, because there are no contradictions. We may have redundant information. Here we see that we're given that A is less than J, but we could have concluded that A is less than J by transitivity because we know that A is less than D and D is less than J, so transitivity implies the AJ edge there. And there are many other transitive edges that we could add to this graph. So we could view this as a partial order where we fill in all the transitive edges. But to actually do that computationally, that takes a long time. So I want to think of it just as a DAG. We may or may not have transitive edges. It's an arbitrary DAG. So we're given this, and now we want to do comparisons to extract the total order, which in this case is the alphabetical order, and we'll come back to that. All right. So if we have a DAG, the fundamental property of DAGs is that they have no cycles and they all have total orders. You can order the vertices in many ways so that every arc goes from a smaller vertex to a higher vertex in a total order. So let's ask a different question. Given a DAG like this, how do I find any order consistent with the edges? That's a topological order. There's some number of topological orders. We have to pick one of them because that's ultimately the answer to our sorting problem. So we can extend the sorting lower bound to this problem. The logarithm of the number of total orders, topological orders, which I'm going to indicate by t here, the log of t, that's a lower bound on the number of binary comparisons we have to do to solve the sorting problem. That's a function of the information we're given. So now the question is, can we in fact come up with an algorithm or maybe an existential construction to show that we can sort the vertices in a number of binary comparisons that's logarithmic in the number of possible topological orders. So let me say a bit about the history of this problem because it's kind of interesting. Mike Fredman, who was a classmate of mine both at Caltech as an undergraduate and at Stanford as a grad student, wrote a beautiful paper in 1976. He considered a more general version of this problem in which you're given an arbitrary set of candidate permutations and you need to pick one. So again, this information theory bound applies. If you're doing binary comparisons, you need a log of size of S comparisons to solve the problem. He proved a result which says that you can in fact do it with the lower bound log of the number of possibilities plus linear in the number of items comparisons. But this is an existential construction. What he said was the algorithm in theorem 3.1 requires considerable enumerative information about the set F for its construction. What this means is exponential time, super exponential time. Our goal here is to not only solve the problem with as few comparisons as possible, but to come up with an algorithm that we can actually implement to do it. So various people looked at this problem. Now back to the specific instance of the problem where we're given a pre-existing set of comparisons. Kislitskin, as early as 1968, and also Fredman, conjectured that there's always one comparison, some comparison, that will split the set of possibilities equally enough so that you can keep choosing good comparisons and get your solution in log of the number of possibilities comparisons. In particular, they conjectured that there was always a way to split the set into not necessarily 50-50. You can't get 50-50 but maybe 2/3, 1/3. It's easy to construct examples where the best you can do is 2/3, 1/3. So the conjecture is that for any partial order, there is always a comparison that will split the set of orders consistent with the two answers into 1/3 and 2/3. It's still an open question, but it has been proved for some constant factor. And once you get a good constant factor, you can then apply this repeatedly and solve the problem in order log t comparisons. So Kahn and Sachs in 1984 proved that you could do this for 311, 811 split. And I'm not sure what the best split that is known so far is, but this is good enough to get the bound. But now the question is, how do you find this good comparison? So their result used, again, exponential time to find the comparison. We still don't have a good algorithm yet. Okay, so Kahn and Kim, 1992, showed how to find a good comparison with the polynomial time algorithm, finally, but it uses the ellipsoid method, which I'm not going to describe, but is pretty heavy-duty machinery to solve this problem. And then more recently, Cardinal et al. In 2013 came up with several algorithms that give polynomial time solutions to this problem. No ellipsoid method, it's basically all combinatorial, but still the time required to figure out what comparisons to do is something like n to the 2.5. Now, you can just sort from scratch in n log n, so this is not particularly useful. What we would really like is an algorithm that runs in linear time in terms of the input size, which is the number of comparisons that we've got so far, plus the number of comparisons we have to do, yes? So m is the number of pre-existing comparisons, n is the number of data points, and log t is our lower bound. We're going to need this much time. We'd like a simple algorithm that runs in linear time and does a number of comparisons proportional to the lower bound. That's our goal here. All right. So let's go back to finding any topological order. This is another classic computer science problem. This is something that the Navy and the Air Force and so on had to do in World War II to do project planning. It came to be known as PERT. There are easy algorithms to do it. There was an algorithm published by Kahn, different Kahn, in 1964. We have our DAG. There has to be at least one vertex with no incoming edges if there are no cycles. Let's remove that and call it number 1. Find another source, remove it, call it number 2, and so on. If we keep doing that, we're going to get a topological order. Knuth, in his famous Art of Computer Programming first volume, gave an implementation of this algorithm that actually runs in linear time. What he said was, put the initial set of sources, the initial set of vertices within degree 0 into a queue, pull the first vertex off the queue, give it number 1, remove all the outgoing arcs, see if that creates new sources, put them on the back of the queue, keep going in that way. Knuth and one of his students showed that, in fact, you can get all possible topological orderings if you don't use a queue to store the set of sources, but you use an arbitrary set and pull out the vertices in arbitrary order. All right, so back to our example here. Here's one example. So A and B are sources. They have no incoming arcs. H is also a source. I think those are the only ones here. So we could pull off A and make it first, pull off B and make it second, pull off H and make it third. We pull off H, I becomes a source because it only had one edge coming into it. When I pull off A and B, D and E become sources, so we can continue in this way, removing sources in some order or other. Now, we're not interested in any topological order. We're interested in a specific one because there's some hidden total order that we need to identify. So how do we modify this algorithm to get a specific order? That's easy. We just plug in a data structure to store the set of sources, and that data structure is called a heap or a priority queue. We put the current set of sources into the set. We always pull out the one that's smallest, and we just run the topological algorithm with the heap. I'll call that topological heap sort. That's the algorithm. Now we've reduced our sorting problem to a data structure problem. What do we plug in for the heap data structure? Turns out if you use any standard heap implementation, Fibonacci heap is one example, this gives us an algorithm that's going to run in linear plus n log n time. But this is still not quite what we want because this doesn't match the log t bound. The standard heap data structures are designed for the worst case. So in the 2.5 minutes I have left, let's look at the next step here. So here's the sorted order. We would put A, B, and H, which are the original sources, into our heap data structure. We delete the minimum, that would be A, that goes on the list. The in degree of D goes down by 1, so it goes from 2 to 1. Next, so nothing goes into the heap when we delete A. We then delete B, which is the next smallest. And now D and E are both sources, and they go in along with H. And now H is not the smallest, D is the smallest, so D comes out next, and then E comes out, and so on. That's the process. All right. Now what we need is a heap that has a certain kind of adaptivity property. What is that property that it needs? It turns out it needs something which I'll call the working set bound. So a normal heap, the time to do a deletion is proportional to the log of the size of the set out of which you're deleting the element. I need a smaller time guarantee. So I'm going to define for each item in my heap a working set, which is the number of items inserted into the heap after the given one. So items inserted beforehand don't count. I want the cost of deleting an item to be proportional to the log of the number of items inserted into the heap after it was inserted. Now, two things. Turns out that if you construct a heap, the right kind of data structure with this working set bound, then you in fact get this log t performance. You get an optimum algorithm here. And second of all, it turns out there is such a heap data structure. In fact, there are many of them, but one that I like is the pairing heap, which is a simple kind of self-adjusting heap, which John Iacono proved almost 25 years ago has this particular working set property, which until now, nobody has actually found an application of. So the bottom line is, if we run topological heap sort with a pairing heap, we get a simple algorithm with the desired optimality properties. And there's one little caveat here. The number of comparisons is also linear in the number of items. You have to change the algorithm a little bit and you can get rid of that additive end term. And I'm out of time here, so I will thank you very much.
Thank you, Bob. As we do not have time for questions, maximize your time there very nicely. So our fourth and final speaker of today's session before the day's first coffee break is Ken Thompson. Ken received the Turing Award in 1983 for the development of generic operating systems and specifically for the implementation of the Unix operating system. And as you may have guessed from some of my previous intros, I did ask each speaker about their hobbies and other interesting things they may do outside of their work ahead of this session. And I really liked Ken's reply. So Ken's reply was, I am a programmer. I wrote the beta release of C and the beta release of Linux. So I think this really is somebody who lives and breathes programming. Ken's talk today is entitled A Technical Solution to an Everyday Problem. Ken, thank you.
First off, I have to, I guess, apologize for the title of my talk. Oh, it's not up there. Oh, that's the, I thought they were going to put a title page on. Because the talk was supposed to be kind of secret, and I was going to give a generalized title, such that.
It's up now. It's up there.
Okay, sorry, great. Okay, basically the title says something. And at one point in the interaction between HLF and me about the title, I invented it I never wrote it down, I invented it, right? And then they said, they asked again, and I gave them a different title. And so we had to figure out what the title really was. All right. I am retired more than 10 years now. I live in a very rural area. I live in a town, except it has no center. There's, it's just houses. It has around approximately 1,000 houses, and they are largely empty because there's around 1,000 people in those 1,000 houses. Many of the houses are rentals or a second home or a permanent home. And so this is a rural problem, which is different from either math or computer science. One night, I'm working late, I went to bed, and I found a screen upstairs, broken open, like in breaking and entering. And then I looked out the window, which is onto the roof, and on the roof there was a bag of pistachio nuts, as if someone had come up and I don't know, hiding pistachios on my roof or something. So I looked around, and someone had broken into my pantry, opened a drawer or two for food, and picked a bag of pistachios and dribbled them up the stairs on the roof, and then left them on the roof. So anyway, I closed the doors, cleaned up the pistachios up the stairs, fixed the screen, locked the window this time, and went to bed. And around 5 o'clock in the morning, there was a loud noise. I mean, and contiguous. It wasn't like a bang. It was just noise. And I looked out on the roof because I suspected something. And there was a menagerie of animals, a large number of animals, maybe 20 animals on this little piece of roof, fighting over pistachios. I didn't clean up the pistachios the night before because it was night, it was dark, and I really didn't want to run around on the top of a roof in my tighty-whities. So it was I left it to be cleaned up in the morning, but unfortunately, these animals, there were raccoons and vultures and crows, ravens actually, and on and on. There were a lot of them. So anyway, I chased them away, cleaned up the pistachios. And I thought, well, I locked the screen, I fixed the window, my life is fine now. And the very next night, there was another break-in. It was in the front door then, right? Actually, it's a door onto a deck, and it's a big sliding glass door. I mean, very heavy. You have to pull it to get it open. And I thought that was safe, not locked. I was wrong. I actually heard this break-in. I heard the door opening, and I heard rustling in the pantry. So I ran out, and just in time to see a raccoon and a fox run away out the door that they'd left open. All right. So I fixed the locks on the deck. They didn't get anything, didn't make a mess. I fixed the lock on the door on the deck, and figured it was all over. So I wanted revenge for them breaking in and messing around. And I had to have a heart trap. Does everyone know it's just a trap that doesn't kill the animal, it catches them. You know, it's a trap door. They step on a trigger and the trap door comes down. And I baited it with peanut butter and bread first. Okay, I painted it with peanut butter, not painted, excuse me. I baited it with peanut butter and bread and put it out, caught a raccoon. Here's my very first raccoon here. And next night I put it out, got another raccoon. Next night, and in fact, one night I got 2 raccoons at the same time. And this went on for many nights. I probably got, well over 10, maybe 15 raccoons. I didn't count them. And finally, my fox showed up. I got the fox. Now, the fox is like a family, I don't know, friend. I've never tried to tame her, but I like to have her around. She's, I like her. She's nice. And every few years, she'll come around with babies, and they are just super cute. You've never seen them. And so I did the raccoons. I exported a very long distance, and the fox I just let go. So the fox was a recurring problem, and so I go on with the trap, and I get fewer and fewer raccoons, and I assume that's because the raccoons are disappearing. And I get more and more foxes because it's the same fox over and over and over. So eventually it turns into all fox, right? And the fox is just a really nice girl. She sits there and waits, and I open and she runs out. And it's the price she knows she has to pay for a little peanut butter and jelly peanut butter sandwich. Okay, so one night, this is a side story, a little tiny side story in this. One night, I put the have a heart trap outside my bedroom door, okay, so that I could hear when it happened, and then I could put another peanut butter bed, really quick. I didn't have to wait all night, and let her. And I also wanted to let the fox go quickly. I didn't want her to stay in there for a long time. And I caught the fox again, and I go out there, and again, I'm, barely or not, in fact, not dressed. And early in the morning, it's 2 a.m, and so I opened the have a heart to let her out, and instead of going out, I had accidentally left the door of the bedroom open. and she ran into the bedroom and ran into the bathroom off the bedroom and hid under the toilet. This is her under the toilet. And I couldn't get her out. I really didn't want to. She's not tame, but she's not wild either. I didn't want to stick my hand on there and grab her by the neck or something like that. I was afraid I'd really get bit. Some of these animals have pretty nasty diseases. So I baited what she became to expect, peanut butter little thing. And made a trail of them out the door, and then left her alone for a little while. And so then after a little while, I assumed, well, she's outside and I can close the door. And I go in there and she's behind the toilet with a whole bag of these. And eventually I took all the peanut butter from her and just opened the door so she has no incentive to stay there, and just went to bed and left the door open all night. And in the morning she was gone. So, can't remember what's next. So back to the story. I wanted to know what was going on with the raccoons because I haven't seen a raccoon in a while. So I put the trap out and stayed up all night looking at it, see what was going on. And every time the fox came up, which was like every 20 minutes, I'd run out and chase her away, okay? And finally I saw the raccoon come out, and raccoons learn and are very smart, and they have opposable thumbs. They are, I don't know, it turned into a one-on-one between me and the raccoon was winning. The raccoon would come into the trap and very carefully avoid the trigger, reach over, get the bait, and leave, and so left the trap open. So at this point, it was now a challenge. And so I modified my Have a Heart trap to be computer controlled. It had a little solenoid kind of motor to trigger the trap. The original trigger was just sitting there, I disconnected it. And so the computer controlled the slamming of the trap. And I put laser transmitters and little photocell receptors and I had room for 8 of those. And I also put a little speaker in there to make noise. Now I figured that if the somehow I hoped that the computer could tell whether it was a raccoon or a fox. And if it's a raccoon, it slams the door. If it's a fox, it makes a noise, and the fox runs away. Okay, so okay, I probably won't go more farther than that. I worked and worked and worked at it, and I couldn't tell whether it was raccoon or fox for good, and I never caught the fox, or the raccoon. And then life settled down, and what happened was that one of 3 things happened. That I thought it was a fox, and I triggered the trap, or noise, the fox ran away, or I miscalculated that it was a fox or raccoon, and I catch the fox. But then there were 2 more things that happened. One was that somebody, somehow, something came in, took the bait, left, and the computer never saw it. And it's pretty hard to see how that many lasers, it's like one of these spy movies where they sneak under and, go over to steal a diamond or something. And the other thing that happened is that the bait was gone and the computer didn't see anybody. Now, it just couldn't happen, that, or the bait was gone and the trigger was slammed. And anyway, I couldn't understand these 2 problems, right? So I worked and worked on it and tried different arrangements and different things. I adjusted the lasers, I tried again. And finally I found out what was happening, that it wasn't a raccoon or a fox, it was mice. Mice would go through the holes in the side. Sometimes they'd catch a laser and I'd trap them, but then they'd just eat the food and walk out. And sometimes, anyway, so it was a mouse. And so I tried to, instead what I did is I put a mouse trap in the trap. And let me see what's next. Oh, that's the whole thing. Anyway, I put a mouse trap in the trap, and I catch a mouse. And next day I do it again, I catch a mouse, and it never stopped. You know, it outlasted me. And I figured that there's more mice outside the yard than I could, you know, get back to the original problem of trying to catch a raccoon in the trap. So at that point, I gave up, called it a total failure, and never had. About once every 3 years, the raccoons break in again, and so I start over. How am I on time? Okay, any questions? I'm done.
This doesn't happen often, but I honestly don't know what to say. That was very entertaining, very enlightening, and I think the title worked. I think that was a technical solution to an everyday problem. I think it was a very suitable title. So that just leaves me to say thank you to all 4 of our speakers for this morning. We can just give them all a final round of applause to all 4.